Hello. In the QCAA method syllabus, there is a very not that used point on using limits. And the thing with limits is that these are usually seen in tech active papers. And the purpose is that they pretty much want you to plot the points. They want you to plot this graph, and see, as usually as x approaches 0, and they'll put x on the bottom, or the variable that approaches 0. They'll put x on the bottom, and you kind of have to plot this, and you'll end up with a graph that looks something like this, and then it will have a point here, a hole, which will be a white circle around, or just a blank circle around it, and then you can kind of find the point, because you can kind of just estimate, because you can't really get a solution for this if you put 0 on the bottom, but you can estimate it by plotting it on a graph. But the thing is, this takes a long time. This is a lot of brackets work as well, putting it into a calculator. You need to do, if you wanted to plot this, for example, on a TI-84, you'll need to do y equals 2 up, open brackets, 2 up x minus 1 close brackets divided by x. It's just very tedious, and you need to adjust your windows and stuff like this. So there's another method of solving these kind of questions, limit-based questions, which are limits because, yeah, they can't really reach the variable that they want, but it's a lot easier, and it's a thing called L'Hopital's rule. L'Hopital's rule. And this pretty much allows you to do limits like this, but tech-free, and it's significantly faster. So the equation for L'Hopital's rule is as follows. I'll just write it over here. So it states that limit as x approaches c just being any number pretty much, just to show the rule, of f on x over, let's just say g of x, is equal to that same limit as x approaches c of f dash x over g dash x. Now what this means is pretty much that if you have your limit, but then you take the differential of both the top and the bottom, it will still give you the same answer. And for example, I have this question here that I have written. So what I'll do is I'll erase this, and I don't really need this top part. You really know how limits work. So I have this written here. So all I'm going to do to find this, because I could plot this on my calculator and find the point that it intersects, 0, whatnot, but it takes too long. I'm lazy. So what I'll instead do is I will take the differential of the top, d over dx of the top, and then d over dx of the bottom. The reason this isn't taught is because it's not in a syllabus, but this is just a significantly faster method. So all you need to do is take the derivative of the top and of the bottom. So now, when you take the derivative of the top, right, so let's just say the top equals 2x minus 1. So you know that when you take the derivative of this, I'm just going to move this over here for a second so we can focus on this. When we do this, the derivative of the 1 is just going to cancel, so it's just going to turn to 0. But when you do the derivative of 2 to a power x, or any value to a power of x, like let's just call it a to the power of x, if you take the derivative of this, it's going to give you this a to the x back, but multiplied by the natural log of that number. This also isn't in our syllabus, but it's very simple, and it follows this rule every single time. So any number to the power of x, the derivative of this, is just going to equal the same number, so 2x multiplied by ln of 2. That's it. So it's just the natural log of this, 2, and then, yeah, there's not even an x involved in this part. It's just the exact same thing multiplied by the natural log of the base. That's simple. So this top is just going to equal 2x times ln of 2. So let's just put, and then the bottom d on dx of x is just going to give you 1, because, yeah. So let's just rewrite this. So this equals the limit as x approaches 0 of, so the top, which we have here, so 2 to the x ln of 2, divided by, and then the derivative of the bottom, which is just 1. So it's the limit as x approaches 0 of 2x ln of 2. Now, because now we can sub in 0, because we won't get an invalid answer, because our denominator's gone. So we can just sub 0 into here. So what we'll do is we'll go 2 to the 0, ln of 2. 2 to the 0 is equal to 1, so this will just equal ln of 2. That's your solution. If you plot that on your calculator, I guarantee you'll get the same answer. It's just a very simple way of doing these type of questions, because these questions take you a long time. There are many ways of doing it. I think you can use the delta table something on your calculator also. A friend showed me. But just using L'Hopital's rule, significantly faster. Very, very, very much faster. And the most complex derivative you'll probably get, I don't think you'll get a sine one. But the most complex function, like let's say limit as x approaches 0, that you'll get is this one from just then, 2x minus 1 over x. The most hardest derivative you need to take is something like this, and you know all it is? All the derivative of this is equal to? All the derivative of that is equal to is just ln of the base, just multiplied by the exact same thing. That's it. 2x. So it's just going to be that. So now I've also got another question, which was from the QCAA External Assessment, paper 2, over here. It was a multiple choice question. The reason it's multiple choice is because they expect you to just do it on your calculator. That's all they expect. They expect you to do it on your calculator, there'll be no working out, and you'll just be able to circle an option and move on. But if we do this, so 12h minus 1 over h. So let's go, so this limit as h approaches 0, as it says in the question, of this, 12h minus 1 over h. So let's just use L'Hopital's rule, so we can take the differential of the top and the bottom, d over dx of the bottom. I mean d over dh, I'm sorry, d over dh, because we don't have any x, we have h though. So you know that the d on dh of 12h minus 1, so your 1 is going to disappear, so and then you're going to have the 12h, but the differential of 12h is just ln of 12 multiplied by the exact same thing, h. So just natural log of the base times the same function. So this is just going to equal limit as h approaches 0 of, so the derivative on the top, which is just this, so ln 12 times 12h, divided by the derivative of this this variable is just going to be 1. So this is equal to the limit as h approaches 0 of ln 12 multiplied by 12h, but we can sub 0 in now, as just going to equal ln of 12. That's going to be your answer. If you don't have your the answer for ln of 12, you can just grab your calculator out, but see, this is just significantly easier than plotting it. All you need to do is just calculate ln of 12, which is going to be 1 second, is going to be equal to, this is going to be equal to 2.4849, which is approximately 2.5. This is your answer. Thank you for watching. This is just a very simple way on how to do these questions tech-free and significantly faster. And just a small refresher before I conclude. L'Hopital's rule. All you need to do as your limit x approaches any number of your functions, so just your function on the top and your function on the bottom, because these are two different functions, you just take the derivative of both of them, derivative of both of these functions, and you'll still get the same answer. You'll still end up with your answer. It just makes it so it's solvable. Thank you for, and I hope you consider this, because it's a very easy way to save time. Thank you so much.